Remember last time I asked you the question, does friction always slow things down? Kinetic friction on an object from a stationary surface does always slow down an object. So if I take this textbook, for example, and I slide it on the floor, it slows down and eventually stops, and that's kinetic friction, which slows it down and stops it. But sometimes the surface is moving. So it's possible, like for example, here's a good one. John has set up this cloth on top of the table. I can pull it along, I accelerate it. So friction is actually speeding it up. Does that make sense? You're supposed to be able to do it, and does Brian do it and the book stays on? You got to pull it faster? I'm pretty bad at this. Whoops. So we're supposed to be proving the opposite thing. But I think that I proved just what I was trying to say. I want to see a better magic trick here. All right. Okay. All right, much better. But even then, did you see it move just a little bit? It sped up, right? So even with John's skills, friction can still speed things up. Why does friction exist? Well, I think it's because every surface, no matter how smooth it looks, will have, I guess the table probably has like hills or something, stalagmites or something, and then and even the book probably has stalactites. And so as they're trying to move sideways relative to each other, those hills and valleys will collide into each other, and probably it's really just the normal force between those microscopic things, irregularities that causes the friction force. It does generate heat. Okay, so that's you in the infrared. So John has a camera which detects infrared radiation, and so what that is, we see light in the visible spectrum with our eyes, but there are lots of different forms of electromagnetic, there's a big delay on it. There are lots of other forms of electromagnetic waves, light being one of them. If you go to longer wavelengths than the light that we're capable of seeing, then it turns out that any warm object is an emitter of infrared radiation. And so we were all like little light bulbs or something. So the reason I can see you right now and you can see me is because of the reflected light that's coming from these lights. If we turn off the lights, we wouldn't see anything. But this is not reflected light. This is generated light by the heat in your body. So it means you're a bit warmer. And can we aim it at me or the floor? There is a physics purpose to this that's relevant to that. So there's me. So what I want to do is stand over here. And now I'm going to walk away like this. Do you see the trail? Okay. That's the heat. So that's what kinetic friction is doing, is it's taking away the energy from me. It's tiring to do that, and it's leaving a trail of heat on the floor and on the bottom of my shoes. I don't know if you can see the bottom of my shoe, that's probably also heated up. Yeah, you see that warm spot on the bottom of my shoe? So both surfaces are generating heat there, and that's where that kinetic energy is going. Okay, nothing is smooth. And then there's an equation for kinetic friction, luckily, which is really good. Sliding friction on a surface is this kinetic friction. Many experiments have shown, so this is the weird thing. You would think that since the reason for friction is just because nothing is smooth and these microscopic surfaces have, irregularities, that you would never be able to know what the friction is. But it turns out engineers have found this approximate equation. And it sort of comes out of nowhere. There's no real motivation for it, but the idea being if you push harder between the two things, like the normal force is bigger, you get more friction. And there's sort of this proportionality constant. So N is the normal force, and this number right here is called the coefficient of friction. It's called of kinetic friction, actually, because there's something else called static friction. And so it's a dimensionless number. It's usually between 0 and 1. 0, and 1. So 0 would mean that there's no friction force no matter what the normal force is, so very slippery. And 1 would just be when the normal force is equal to the friction force. It doesn't, for some reason, go over 1 very often in the tables that I have found. Like there's a table in your book which just lists the coefficients of friction. So like rubber on dry concrete, for those two surfaces, engineers can measure this proportionality between the kinetic friction force and the normal force to be around 0.7. Rubber on wet concrete, 0.5. Wood on wood, so you can see like wood on snow, like for skis, it's 0.1. That's pretty slippery. Okay, and it goes all the way down to Teflon. Okay, they actually designed Teflon to be slippery so that your eggs don't stick to the surface of the pan. And you get down to 0.04 kinetic friction. Is the block accelerating? If so, what is its acceleration? So that's not too hard to find. We already did this, right? So we found that, what was it, exact same thing. You've got, this one is F equals 5 newtons. This one backwards, Fk equals 10 newtons. So I think what you're trying to say is that the acceleration in the x direction is F net in the x direction divided by the mass, right? And so you would say that it's going to be the F minus the F sub k divided by m. So I think it would be 5 minus 10 divided by 10.2. So yeah, I get a sub x is equal to negative 0.49 meters per second squared. But you already were told that that v sub x is equal to positive 5 meters per second. So this is a case where v sub x is greater than 0 and a sub x is less than 0, the opposite sign. So what does it mean? Thinking about what happens when an object is in contact with a surface but it is not moving relative to that surface. So for example, this frog, he's got sticky feet or something, he's on an incline, so if there was no friction, I think the frog would slide down the hill. But there is friction and he doesn't, so the friction force here, I have to draw it on there in the free body diagram, something to keep him in equilibrium and keep him from accelerating. And so the frog doesn't move. There is the object and the surface are kind of locked together, and this creates a force of the surface on the object perpendicular to the normal force called the static friction force. And there's no equation for it. And also you can't find the direction. The only way that I would find the direction is I always tend to think to myself, which way does the object kind of want to slip if there were no friction? And so for me, this frog, I think, well, he would just go down and to the left. He would go down the hill. And therefore, I know that when I draw my free body diagram, I have to do the static friction opposite to that. I know it's perpendicular to normal, but do I do it up the hill or down the hill? I get this question all the time. So just think, does the object want to slip up the hill? In which case, it goes down. If it wants to slip down the hill, then the static friction goes up. Video kind of showing this a little. For a block, that if you leave it alone, there's no static friction, but if you pull it with the spring scale, so she's now going to pull it to the right with the spring scale, and you can see as she's pulling, it's not going anywhere. So whatever force here that she's pulling to the right, there must be somehow a static friction force being generated in the block. It doesn't look like anything's happening on the block, but until it slides. I think she's trying to go, she's pulling and pulling and pulling, and then as you're saying, I think eventually there's a point where it starts to slide. There are some equations for some forces, and really there's two big equations we use again and again in this course. Gravity, which is mg, and kinetic friction, which is mu sub k times the normal force. Normal force, tension, and static friction, there's no equation for them. These are self-adjusting forces which come as needed. Normal force is just whatever you need to stop yourself from falling through the floor. Okay, if I pick up this table because there's a normal force on my feet, well, I pick up the table, the normal force on my feet is just self-adjusted to be higher, right? I put it down, it's less. So, okay, whatever it takes to keep crashing through. Tension is whatever it needs to keep the fish from getting away, okay, before the string breaks. Static friction is whatever is needed to keep the object from slipping. Now, they all probably have a maximum, and there is an equation. They come right at you in the book with this equation for the maximum static friction. for some reason, but don't get confused. Don't look for an equation for static friction. There isn't one. So, if there's no equation for it, what do? You draw a free body diagram and solve Newton's second law for the accelerations that you probably know from something else.
So when you're trying to find this amount of static friction, is it always going to be smaller than the coefficient of friction times the normal force?
Yes, exactly.
Okay.
So that's a good point. There are some experiments that you can do which show that you can measure kind of a maximum. So if we pull that same block on a table, a mirror, and rubber, there's this maximum where it starts slipping. And that'll be different, a different maximum for different surfaces. And, well, it's the same maximum if you have the surface on different areas, okay? But if you increase the mass, increase the normal force, you also get a different maximum static friction. So it turns out, oddly enough, that there is an equation for the maximum static friction. There's a limit to how big the static friction force can get. If you push hard enough, the object will slip and start to move. So the two surfaces don't slip against each other as long as there's this inequality, and this is how I calculate the Fs max. So static friction is between 0 and this value, depending on the situation. N is the normal force, and mu sub s is the coefficient of static friction. There's also so this is the other column in this table. Static friction is the confusing one, so I usually show that last. Kinetic friction is the easy one. You just multiply normal force times the coefficient of kinetic friction. You always get the kinetic friction. Static friction has this maximum. So if you're given a question where something's just about to slip, that's when you use this thing. Let's talk a little bit about drag force. This was on this morning's pre-class survey. There's this idea that as something is moving through the air, there is a resistive force due to air resistance, which is, well, it's opposite to its velocity, and it is proportional to its velocity, I think, squared or something. So the faster you go, the more force there is from the air slowing you down. So if something is falling, the faster and faster it goes, the bigger and bigger the drag force becomes, until they eventually become equal, and then there's no acceleration, and so the thing reaches what's called a terminal velocity, when Fd equals the weight. And it turns out, when you jump out of an airplane, which I've done actually, you jump out and for a little bit you feel weightless and you're like, whoa, I'm falling. But then it gets really, really windy and you feel like you're just sitting there, like actually lying down on a bed of wind that's just blowing. And that's exactly what's happening. It's like you're lying on a bed, but it's wind because you're not accelerating down. So this is a little plot of the frictional force applied to an object versus, I guess, time, as if you were to increase the force somehow. So what we're going to do is we're going to increase that force by changing the angle of a track. But, of course, as you're increasing this external force, the frictional force just increases sort of at this 45-degree angle. There's the same amount of force that you apply equals the frictional force. So the static friction just equals the applied force. Until it gets to some maximum, mu sub s times the normal force, and then it starts slipping. And when it starts slipping, the frictional force is now less, because mu sub k times n is usually a little less than mu sub s for the same normal force. So what I'm imagining is you're sort of pushing something along. And so then, if it's going at a constant speed, this friction, or it could be accelerating, could be eventually going at a constant speed, but at some point, but for all this time, the frictional force is given by this just mu sub k times n. At what angle is it just about to just slip? So what I'm going to do is put an angle theta here. Assume that the block is at rest. It might be filled with something, and this has got some mass m. And mu sub s is the coefficient of static friction between the box and the surface. So that you could find from a table somewhere, for example. If it's just about to slip, then you can use the equation for static friction, the maximum. What that means is that the static friction equals Fs max, and we do have an equation for that. It's mu sub s times n, where the n is the normal force. So let's draw a free body diagram of the mass. So it looks like this. There's a normal force acting up, and to the right a little bit because the thingy is tilted. There's the static friction force is going to be preventing it from slipping down the hill. So it's up and to the left a bit, static friction. And then the gravity force is acting down like that. And I think those are the only forces. And just let's remind it, that is the theta there. And what I think I'll do, I'll tilt my axes again. There's a lot of ways of doing this, but if we tilt the axis like that, y this way and x this way, then what we've got, if we do our little components of forces, x and y, the forces are N and F sub s and mg. The normal force is only in the y direction, and it's 0 in the x direction. The static friction force is only in the x direction. I guess it's only in the negative x direction, negative mu sub s times n, and there's no y component. And unfortunately, the gravity is the one with the diagonal. So if we do the mg, I think this is theta here. This will be the weight, negative the weight in the y direction, and this will be the weight in the x direction, which is positive. So I think we get mg times sine theta here, and negative mg times cos theta here. And these net forces, F net, has to equal 0. So what this means is that F net, say in the x direction, is negative mu sub s times n plus mg sine theta. And also F net in the y direction is equal to the normal force minus mg cos theta. And so actually n equals, and this is equals 0, this means that n equals mg cos theta. So we can solve for the normal force using the y component, and we can plug it in to this x component. So if this equals 0, then we've got negative mu sub s times mg cos theta plus mg sine theta equals 0. You end up with, I think there's a lot of cancellations here now. The m's cancel, the g's cancel, and you get basically mu sub s times cos theta equals like sine theta. And so mu sub s equals tan of theta, and so theta is tan to the minus 1 of mu sub s. I have these tracks here, and these boxes that John has set up can slide along on the track. We'll put it on the video for you so you can see it. Yeah, there we go. And there's different boxes with different surfaces. So this one has got some sort of Teflon on it. This one has got, I guess it's like a felt. You can't really see it there. And this one has like a cork surface on the bottom. So the 3 different boxes have 3 different surfaces. And if you tilt it up by raising this end, then at some angle, they'll start to slip. If I go, whip, that's way up there. Once it starts to slip, whoop, I'm going to lower it till it just about doesn't want to slip anymore. There we go. So that's kind of the angle where if I go any higher than that, this box is going to slip. If I put a different kind of surface on, like this felt surface, then I can pick a different angle. Go a little higher, a little higher. Where does it want to go? Oh, there we go. There, it started going. So I got to lower it, stop it. You have to kind of let it not be moving to find that right angle. So this has got a higher coefficient of static friction. It's always just going to be tan to the minus 1 of whatever this angle is. But what's interesting, too, is that we can load up this with more mass. Oh, it does want to slip. It's still... Maybe I've got it too high. The idea is that if you have more mass, then there's higher normal force that increases. It increases 2 things. It increases the maybe we should do it with the. Let's try the cork here. It'll increase that component of the force of gravity pulling it down the hill, but it also increases the normal force. So what we want to see is that the mass doesn't matter. Where's the cork? So that's slipping a little bit. At this angle, doesn't want to slip. If I add more mass, I say, let's double the mass here, and see if it slips. Also, does all right, so excellent. Drag force. Okay, so this is this air resistance. Basically, anytime you're moving through a fluid, there's going to be some dissipative resistance to motion through that fluid. And air is a fluid. It flows, and we go through it. There's a lot of turbulence that can get formed. So in order to really solve for what the drag force is while you're going through a fluid, you need fluid dynamics equations and numerical simulations. But it turns out, when the fluid is air, the object that's experiencing drag is larger than a marble, roughly, something like that, and traveling faster than about 1 meter per second. Then there is an approximate equation for drag force, which is given here, 1/2 c rho times a times v squared. So rho here, this little, it looks like a p or something, that's the density of air. Rho is equal to, it comes up a lot in the textbook, 1.2 kilograms per meters cubed. Something I would give you, but good to know. C is some sort of dimensionless drag coefficient, which depends on the shape of the object and what kind of surface it has. So like a golf ball will have little dimples on it. The dimples make a difference to this drag coefficient, or if something's triangular, or if it's a piece of paper, has a different shape than a sphere. A is the cross-sectional area of the object, which means the kind of area that you see perpendicular to the velocity that's going through the fluid. And then you square it. Okay. And this is like a table of various drag coefficients. Sphere has 0.45. A skydiver has an approximate coefficient of 0.7 if you're going feet first, or if you're kind of lying horizontal on the air, or like this on your stomach, it's closer to 1. A circular flat plate can have a higher than 1 drag coefficient, but you just measure these. Engineers measure these things. And we can do an example. Let's say we drop a tennis ball from the top of the CN Tower. How fast does it get before air resistance stops it from accelerating? And don't forget, rho of air, I'll just say, is 1.2 kilograms per meters cubed. We're going to do everything carefully in SI units here. But basically, if this is the CN Tower, you throw the ball, it's going down with some speed v. So maybe initially v0 equals 0. The gravity here is 9.8 meters per second squared. But this thing is not in free fall because we're not neglecting air resistance. We're including an upward drag force as it falls. So if something's just falling with 9.8, it has a very simple free body diagram. It's just mg down, and that's it. Now there's an upward drag force, and so the free body diagram of the tennis ball looks like this. There's the dot. So there's mg acting down, but now there's this force Fd acting in the upward direction. And so I would say that Fd equals 0 when the initial velocity is 0. Starts off, there's no drag when something's not moving. But then as it gets faster and faster, there's this v squared term, so it's going to increase. So Fd increases as v squared increases, because there it is, until I think it'll get to a point when Fd equals mg, so the weight equals the drag force, then the net force is 0, and so it stops accelerating. When the magnitude of the drag force equals the magnitude of the weight of the ball, then the net force is 0, and so acceleration is 0, and so v is constant, and so this is called terminal velocity. And we can calculate how much it is by just saying, let's say Fd equals mg, so 1/2 C times rho times A times V squared is M times G. Let's try to solve for V. 2 times M times G divided by C times rho times A is equal to V squared. I will also say that the cross-section area of a sphere area is that of a circle. And the area of a circle is area is equal to pi r squared. So we can plug that in there. And we get V is equal to the square root of 2 times M times G divided by C times rho times pi times r squared. So I've got 2 times 55 times 10 to the minus 3 kilograms times 9.8 divided by 0.53 is the drag coefficient times 1.2 kilograms per meter cubed is the density of air times 3.14 is pi times, and then this is 3.3 times 10 to the minus 2 squared. If you guys can kind of read that or figure it out. And when I plugged it into my calculator, I got 22.3 meters per second. So a real tennis ball, as you drop it, now it's kind of weird because you have to accelerate to that point, and as soon as you get to that point, you're not accelerating. So I think what happens in real life is that it speeds up at first, like with 9.8 meters per second every second, but as it gets closer and closer to 22.3, it just gets closer and closer, it asymptotically approaches this terminal velocity. After about 3 seconds or so, it's not really speeding up at all, or not much. And you can actually, if you want, write on your rate sheet just this equation, because this I find with the drag questions you actually get for problem sets and for term tests and things, this is the equation you end up using. You don't really use anything else. Because it's complicated, right? If you try to use this on projectile motion, you end up with a x component and a y component of the force, and you can't solve it in any way except just to do a simulation. And I figured out, I guess, you can plug in different masses and different areas, and you can easily find that smaller creatures fall have a terminal velocity that's less. So there is this whole thing, Stokes' law. So if an object is very small and it's traveling through a dense medium like a liquid and going very slowly, then you have a drag force, which is, it's also opposite the velocity, but it's proportional now to the speed. And I tend to think of things like bacteria or something that are falling through a liquid or something, and there's a drag force there. So, and you got to use the viscosity of the liquid, which you'd have to be given as well, which has a kind of a weird units. I want to get on to elasticity. That's the last thing that's in chapter 5. Basically, you're talking about all the different kinds of forces that engineers can give you. And certainly, friction is one, and these coefficient of static and kinetic friction, engineers make these tables. Drag force is another one, and you can get coefficients, you can get these drag coefficients. Well, another one is the elastic force. So if you have a spring attached to a box on one end and the wall on the other end, then there's some equilibrium length of the spring where it kind of wants to be, the length it wants to be. If you stretch it beyond that length, then if you compress it to less than that length, then the spring exerts a force on the box, which is to the right in this case. Or if you stretch the spring, then the spring pulls in on the box. So that's the idea. I've sort of drawn the delta L's here, but this is the equation called restoring force. It's given by what's called Hooke's law, which says that there's some constant, sometimes called the spring constant, it has some units of newtons per meter, and it gives the magnitude of the force. So it doesn't give direction. You just know this restoring. The restoring force tries to get the object to go back to when the spring was in equilibrium length. So in the top two drawings, the spring is compressed, and so it tries to push the box back towards delta L equals 0. In the middle diagram, when you have delta L is 0, then there is no spring force. And if you stretch the spring, then that force grows again, but it's pointing in the opposite direction. So this gives it's a magnitude equation. It's also approximate. I don't know if anyone's ever played with springs, but if you overstretch them, like you overstretch your slinky, then it doesn't really work anymore. So Hooke's law is approximate, given for small values of delta L. This is the stress versus strain stuff. So this was from this morning's pre-class survey. What's the best description of stress and strain as introduced in this section? So stress is an amount of external pressure, and strain is an amount of it's a resultant deformation. So here's the basic idea. You can cause something to deform by applying a force to it. And we call this thing stress is the force divided by some characteristic area of the object. So you get newtons per meter squared. And then strain is how much the object deforms. And so it changes its linear dimension in some way and in proportion to how big the object is. So you do kind of like a delta x divided by x, like x0, the equilibrium length, and you get a strain which is dimensionless. And then there's something called the elastic modulus, which you look up in a table that the engineers give you, and that gives the rigidity of the material. And a higher elastic modulus means that the deformation is less for the same applied external force. So this is sort of this approximate equation, which is that strain is equal to the stress divided by the elastic modulus. And there's a few different examples of this. First one is stretching, or it's called tensile or compression deformation. When a solid object is either stretched or compressed along its length, it can experience a slight change in that length. So here we have delta L is the little change in length. L0 is the equilibrium length, I guess, when there is no force applied to it. And there's the force, and then there's the cross-sectional area of the object. This is A right here, which looks like a circle, I guess, in this. If it's a cylinder or something, we'll have a cross-sectional area of pi r squared. And then Y is this Young's modulus. So, and you can look that up in a table somewhere. So let's do a quick top hat question. And here's a sort of a table from your book of some of the elastic moduli that come up. You've got this thing called shear modulus and bulk modulus. So basically shear modulus is when you've got a sideways force acting on an object, and I like to think of like a box of Jell-O or something like that. You press sideways on it, it shears the object by some distance delta x, and you're applying this force over a top surface that has some area A, and it has some width that is L0. And there's an equation there on which you use shear modulus. And then bulk modulus is when you've got an object that's surrounded by force on all sides, and there's sort of an inward pressure force. And this pressure is force divided by area, and you've got a bulk modulus. So some really good questions this morning. Is stress pressure or just force per area? And the person actually asked, is this the same way, in the way that torque is a force times distance, but it's not an energy? So that's a fantastic question. So stress is an external force applied over some area, and so it certainly does have the same units as pressure, force per area. But it's not exactly a pressure. I think it's a bit subtly different, except in the case of bulk modulus, in which case it is exactly the pressure. So it is similar. On the other hand, I would say that torque and work are not at all related. They just have coincidentally the same units. Another fantastic question this morning is why no bulk moduli are given for gases? Does the bulk compression equation apply for gases? So no, you completely don't use that equation for gases. For a gas, you use the ideal gas law, which is equation 13.37. This is a completely different equation, where the volume goes to zero for zero pressure, right? Sorry, wrong. Pressure goes to infinity for zero volume. So for gases, you use something totally different. Here's a sort of weak analogy, which you may have picked up on with this whole strain and stress business, is that strain and stress have meanings to us outside of physics. So maybe stress is something like external that's being applied to you, and strain is how much you react, perhaps, to that. So if you have a low elastic modulus, a small amount of external stress can cause you a lot of strain. You're kind of flexible in that sense. High elastic modulus means you can handle a lot of external stress without much strain on your on your mental health. Maybe you're more rigid, you just kind of push through things. So. But these are these elastic moduli, and what I talked a little bit about tensile stress, but let's talk about shear and also volume stress. So shear modulus is this delta x. If you push something kind of sideways to its length, it twists a bit perpendicular to its length, called shear deformation. So here's a drawing of a 160 kilogram crate, and it's hanging from the end of a steel bar. And we have from our little table there, the shear modulus for steel is 80 times 10 to the, don't forget to times 10 to the 9 newtons per meter squared. The times 10 to the 9 is inferred in this table, but that's important that you don't miss it. You've got L0 is this length of the bar, and that's been given. L0 is equal to 0.10 meters. And then they also tell you the cross-sectional area. So that is this area, A, which equals 3.2 times 10 to the minus 4 meters squared. And I'm going to say that the force is equal to mg to support this thing, and m is equal to 160 kilograms. And also the S, the shear modulus, is 80 times 10 to the 9 newtons per meter squared, or I guess 8 times 10 to the 10. And what we need is, like I guess this would be your delta x here. You need delta x. So you just use delta x is equal to 1 over s times f over a times L0. I'm going to use mg as your force, L0 is on the top, your shear modulus is on the bottom, and your a is on the bottom. So 160 kilograms times 9.8 times 0.1 divided by 80 times 10 to the 9. You've got to be careful typing that into your calculator. Times 3.2 times 10 to the minus 4. And hopefully you get 6.1 times 10 to the minus 6 meters. A very, very small bending of the steel bar, like a microns or something. So it's sort of plugging in. And then bulk modulus, same sort of thing. But now you've got actual pressure. So a surrounding pressure force is inwards on a volume of material. It experiences a reduction in its volume, assuming that it is not a gas. If it's a liquid or a solid, then there's a bulk modulus that you can refer to figure out how much it deforms, delta V divided by its total volume V. So, for example, you've got the ocean here, and the pressure increases by 1 times 10 to the 4 newtons per meter squared for every meter of depth beneath the surface of the ocean. I would say that something like this pressure at depth D is equal to D times 10 to the 4 newtons per meter squared. And this is equal to F over A, the pressure. So you're trying to find D is question mark, and here's your little cube down here. And we have that V0 is the x cubed. It's the volume of a cube, so it's 10 to the minus 2 meters, all cubed. So I think V0 just equals 10 to the minus 6 meters cubed. 3 times negative 2 is negative 6. And delta V was given as 10 to the minus 10 meters cubed. Let's use this equation. Delta V is equal to 1 over the bulk modulus times F over A times V0. And let's solve for F over A here. So we can find that. I think we get F over A is equal to delta V times B divided by B0. So it's 10 to the minus 10 times the bulk modulus, which is 30 times 10 to the 9. Don't forget the times 10 to the 9 here. And then divided by 10 to the minus 6. And you get F over A is equal to 3 times 10 to the 6 newtons per meter squared. And so D is your F over A, your pressure, divided by this 10 to the 4. So I get 300 meters down. And both of these might be useful on the upcoming assignment. Okay. Also, there was, I don't know, Song, if you're here, but there was a good question on the email yesterday. I did not quite understand the top hat question. One, this is from Friday's class, in which I was saying that the friction is greatest in case C. You know, and I guess he was wondering why the kinetic friction isn't less than the static friction. So, and first question was, if the friction on box C is the same as the pushing force of 130 newtons, then how could it be moving? And I would say, remember, the net force means that if the net force is 0, the acceleration is 0. That does not mean that it's not moving. If it has some initial velocity, it keeps that constant velocity. And that's exactly what's happening here. The reason it's going at 1 meter per second is not because of the forces, it's just because it already was going at 1 meter per second for some other reason. So there's no equation for initial velocity, right? You have to find it from the situation. And then, in regards to static friction versus kinetic friction, isn't it true that static friction is always greater than kinetic? And I would just say that's not at all true. Static friction can be 0, right? It's whatever is as needed. So the way I would kind of see it here is that for these two cases, maybe this is A, this is maybe B. She's just pushing and it's not moving. But then at some point it does get moving. She must actually push it greater than 130 newtons. But at this point, C down here, she's pushing with 130 newtons and it's just cruising along at a constant velocity. So static friction is a self-adjusting force. And so let me just kind of review here these big 5 forces, the forces that come up most often in this course. And there are equations for the weight is mg, and kinetic friction. Kinetic friction is always mu sub k times the normal force. But these other 3 forces in the middle, they don't have an equation. They are called self-adjusting forces. And so you can't find them. So the only way you find them is you just balance your forces and use Newton's second law on your free body diagram. That's what you do. And the question is, how do they actually self-adjust? Well, for example, tension. I think what's happening is that as she pulls on this crate, probably there's a slight increase in the length, and this would be from the Young's modulus is how you would calculate it. How much does the string stretch? A tiny little bit. We don't talk about it very much, but the string probably stretches a little bit, and all those little atomic forces, which can be modeled as springs between the molecules in the string, that's what produces that tension along the length of the string. And then it acts on the box. So the string always stretches at least a tiny bit, according to Young's modulus. Normal force, same sort of thing. If you put a heavy book on top of a pillow, you'll see that that pillow sinks, right? But if you put it on top of a sturdy table, you don't notice that it sags, but it must. The table may not visibly flex or sag, but the book must be compressing, and I guess this is sort of a shear modulus, it must be compressing the table a little bit. And that, even the hardest surfaces, even marble, must compress a little bit as you walk on it, if you were able to somehow measure that. So as a consequence, those little springs push back upwards on the book, and that's what provides that normal force. Okay. And then static friction, same sort of thing. You've got 2 objects placed in contact. They don't make a smooth fit. They kind of lock in a little bit. The high points on one surface sort of become jammed against the high points on the other surface. And at the points of contact, the materials will form, I guess the molecules will interact directly with the molecules on the other object. Kind of like the normal force, really. But because of the topography here, it can have a parallel component to the surface. And they can even form little molecular bonds. These bonds and slight bending of the contact points will create the static friction force if that's parallel to the surface, if those surfaces want to slip relative to each other.